In this video, I would like to discuss, after we have already introduced to you how the nonlinear material behavior is taken into account in a finite element formulation for an element, how the computation occurs for a nonlinear process. So we are going to look at some procedures that are used as a standard for the displacement or loading condition and how we calculate the unknown from a problem. We will look at time-independent plastic analysis. So we assume that the goal of the analysis is to determine the nodal displacements and the stresses when a structure is loaded by means of a known external load vector. Now we presume that for the material, we already know from tests the uniaxial stress strain behavior. We also know the Young's modulus. We know the hardening behavior, which is given as HP. And let's say, for example, that this is a von Mises material, von Mises stress problem. Then we also know the von Mises effective stress, sigma E. And we know the yield stress for the material as well. So with all these conditions known to us through testing, we would be able to start from a position at a zero loading state. And when we apply the initial load step, we should be easily able to get to the verge of yielding. So let's say that in this problem, we have an unknown displacement. So U is unknown to us. So this is the displacement. I'm going to use displacement as U. And we need to find out also the stress, and the stress depends on the hardening behavior of the material, right, which we have already described to you before in terms of the yield function. So for a simple case, let's say we start from load point 0, and at the first load step, so if we have step 1, delta R1, we want to arrive at the point directly, which is going to give you the yield stress. Now this might seem like, okay, how do I get this? This is very simple actually. So what you do is that you apply an initial load step, you carry out a linear analysis, and you determine your sigma E for the von Mises condition, which is the effective stress. Now you check how far away you are from the yield stress. So you need to get a certain ratio of the effective as well as the yield stress. So it should be basically equal to 1 so that you can get to the point over here, which we can call point C or whatever, to the point of yielding. And that would become then your step for subsequent load increments, which we are going to follow now for a certain case. Now, let's say that you have an individual sampling point. It doesn't have to be at point C, okay, not necessarily, but just at any sampling point. Let's consider that this sampling point is at state A. Let's just say A sampling point. It's an arbitrary. Let's say that this condition, we will call it as to be in state A. We expect that at state A, your problem is in equilibrium. It follows all the compatibility conditions. Its approximation is quite good. That means your error is quite small with respect to the actual behavior you're looking for. And it follows all the yield criteria and other requirements. Okay, all these things are checked. Now you need to apply a certain load increment, which we can give as RAB, which is equal to a load increment, which will create this structure or this continuum to be now in state B. Now in state B, you can have different conditions that can happen. By adding this external load increment, your state B could, in a certain circumstance, remain elastic. In another circumstance, it can remain plastic. So if A was plastic, then B is also plastic. Or you could have a third condition where you would have a problem make in elastic, plastic, transition. So these are the three conditions that we are going to look at during the course of the few videos now, to make sure that we understand how the increment of displacement is going to occur. So the idea is that for the state A, we have a structure which is in equilibrium. You have an approximate solution which follows compatibility and the yield criteria. You are going to apply a certain load increment delta R, and what is unknown to you is the displacement. So delta U, for example, AB is an unknown.